Hi, folks. I'm Vanessa Sackett. I'm a principal computer scientist at Lawrence Livermore National Laboratory. And today I'm here to talk to you about Flux Framework and Quantum, some of our early work with qrmi. So for those that haven't heard of Flux, it is the workload manager developed at Lawrence Livermore National Laboratory. It combines hierarchical job management with graph-based scheduling. And we have quite a talented team. A lot of the initial engineers that developed Slurm, along with experts in container technologies, scheduling, high-performance computing, and cloud. Now, Flux addresses a lot of what we call post-exasale challenges. So this is the idea that our workflows are becoming much more heterogeneous, demanding more resource types to be run across centers or clusters, and they're dynamic. And so Flux was initially envisioned many years ago to solve some of these problems. How might you ask? Well, first, Flux scales. It runs on really big computers. It is deployed as the system scheduler on El Capitan, the #1 in the top 500 list of supercomputers for now 2 years in a row. Flux also has a hierarchical modular design, and that is the key to its portability, flexibility, and specificity. So what you're looking at here is a visual representation of a tree graph, which is how the scheduler models our resources. So traditionally, you would see, for example, the cluster. The cluster has racks. The racks have nodes. The nodes have sockets and cores. And Flux is able to traverse that graph and schedule to any resource in the graph. And what's so cool about this, what's so flexible and powerful, is that we can model arbitrary resource types and then schedule to them. And that's going to be immensely important for our discussion today when we want to model quantum devices. Flux also enables converged computing. This is the best of both worlds between cloud and HPC from a cultural and a technological standpoint. Here's what that really means. Now, we started this work way back in 2021, and the idea was like, I have cloud, I have something like Kubernetes that has a bunch of features that I really like: modularity, portability, automation, declarative management. But I also really like my high-performance computing features. I want performance, I want low latency, I want sophisticated scheduling, I want the scale. So if we take those two things and we shove them together, the intersection in the center, that is converged computing. And what we're starting to see increasingly is that there's another dimension starting to push in, and that is quantum. So just as a quick example of some of our projects that have existed in this converged computing space, the Flux operator is the first. This is like an application that you install to a Kubernetes cluster that knows how to deploy an entire Flux cluster from one YAML file. So you take your YAML file and you say, hey, Flux operator, I'd like a cluster with this many nodes, with this design. And then basically you apply it and it will create a number of pods, where one pod is the leader with a set of followers, and they're connected via a tree-based overlay network. And so then the idea with an operator is it does something called reconcile. It looks at the actual state of the cluster against the state that you want, makes an incremental change, and then keeps reconciling, making those incremental changes until those two states match. Another really recent piece of work we've done that's really important for the AI ML community is integration of Flux with the Kubeflow trainer, which is sort of an industry standard for training at this point. This allows you to pair traditional scientific simulations that are with AI ML models and to kind of combine those two spaces. It's a really great example of convergence. Now, another really great thing that the Flux operator affords, and it's done this since it was developed in 2022, is elasticity. So many of our workloads are not just static, they're dynamic. You start out with a small set of nodes, you need to scale up, you need to scale down, you need to deploy a different set of nodes. The Flux operator allows you to do that. Now, Flux also, because it is modular, it is made of different components. It is plugins, it is extensions. The scheduler is a different project than the core. It is not a monolithic single beast that you have to like move around really heavily. This allows us to prototype novel algorithms, match policies, because I can take just one small component of Flux, customize it, and then, for example, plug it into Kubernetes or a completely different environment. And so what we've started to realize as we make this transition from traditional HPC into what we think of as this converged HPC center of the future, where we're running coupled AI/ML simulation ensembles. We have dynamism, elasticity, declarative management, is that there's actually another row in this table. That row is related to hardware. We're moving from this traditional HPC hardware into the addition of quantum devices. And if you're kind of staring at this a little bit, you might realize that much of the features that we need to enable science is enabled by the workload manager, which is why this work is so important. And this also represents a shift in our thinking. So some of our early work, which I'll point out here, was really looking at features, taking features from cloud, features from HPC, and making projects that put them together. I will highlight our project called Fluence because this was a custom scheduler plugin that we had this mindset for back in 2021. Now we've moved to this mindset of like, we actually need to think more holistically of the entire environment. And that's also reflected in this update to Fluence, where we have a custom scheduler plugin still, but it uses native gang scheduling, and it has the ability to add arbitrary resources such as quantum devices. So let's talk about that now. What is the journey that we've made in order to get to the demos that I'll show you? So the first thing we decided to do is make Go interfaces to qrmi. This is because, the language of Kubernetes is Go. So it seemed like a logical first step. So this is probably logical. We start with qrmi that has good interfaces in C, and then we make qrmi-go from it. So it's basically these Go bindings. And then with those Go bindings, we can develop them into a custom scheduler plugin in Kubernetes. It could go into a CNI. It could really go into any Kubernetes component or actually the application itself that's using the same interfaces. The next thing we wanted to do is we wanted to be able to take qrmi-go. We wanted to instantiate a fluxion resource graph, and I'll show you what that looks like, that models both traditional compute and quantum devices, ask a request of it to say, hey, resource graph, can you match this need for work that I have that needs this many cores, this many quantum devices, and then get back a match or no, I can't satisfy that request. So we created this particular project, fluxion-quantum. And I need to point out that there's actually two models for quantum resources. There's the idea that I am interacting with remote devices that are accessible via someone else's API, maybe an SSH command. But if you look down at the bottom, the important nuanced detail here is that there's actually two queues. So I might be modeling the traditional and the quantum resources in my resource graph. When I actually make a request with qrmi-go, that is technically going into a queue that IBM owns. It is a second queue. Now, the difference with the second model with local devices is that this is quantum hardware that your institution owns, as in like the freezer with the devices is right there. And when I am, when my scheduler is saying that I get that channel, I have a guarantee of getting that channel and nobody else gets it. So the difference is that there's one graph, but then there's only one actual queue. And the scheduler is both kind of orchestrating the scheduling, but it is also orchestrating the actual execution of the work. And the really cool part about both these designs is that there's one graph either way. The design might look a little bit different depending on what you're modeling, but it is just a JSON file. So let's take a look at what that might be. For our first demo, let's take a look at the fluxion-quantum project, which was our first prototype to take Fluxion, our scheduler, specifically the Go bindings, and then to model quantum resources in a resource graph, which is a JSON file, alongside traditional HPC resources, and then query the graph. And this is sort of emulating what would happen during scheduling. It's just missing the Flux core that's actually going to, dispatch a node. So let's first look at what the cluster graph would look like. We're going to look at comp quantum.json. As I mentioned, the cluster, the modeling of the cluster in a graph format in a tree is just a JSON file. So at the top level, we have a node. So here we have our nodes, and we have a node for the cluster. Under the cluster, we have racks. Under the racks, we have nodes. Under the nodes, we're going to have sockets and then cores. Now, where does the actual quantum come in? So what we decided to do here after our cores, scroll down a little bit, we decided to model the quantum devices on the same level of a rack. And as you can see here at ID 100, we have a node that is called a Q device. This is an abstraction for a quantum device. You can look at the path in the containment subsystem, and that is tiny 0 Q device 0. So tiny 0 is the name of the cluster, and this is quantum device 0. And then under each quantum device, so again, we're in a tree and we're moving down that tree, a child of the quantum device is a QPU. And so we can see that under each QPU, we have the qubit, and then we also have a coupler. So those are the nodes. We have quantum devices and we have traditional HPC. Under the edges, that is a simple mapping of this node is connected to this node. So each edge is going to have a source and a target, and then it's the containment subsystem. And the idea of a subsystem in Flux is generally that you can have different resource types of subsystems. So you may have a power subsystem, you may have a network subsystem. Generally, when we talk about the containment subsystem, we're talking about the core hardware resources. Now, for fluxion-quantum, because this is qrmi-go with the flux-go SDK, we basically build a simple application. Now, I want to point out to you that I am in a development environment. So if you go to the repository, it's recommended to open this up in the dev container. This is where you're going to get the entire environment that is afforded by the dev container, so you don't have to like build Flux locally. I haven't done this yet, so let's see if I can compile it. So as you'll see in the compile command, we're using cgo. We are pointing it to where the flux-sched bindings are, along with qrmi-go, which is built within the container. So that is going to compile fluxion-quantum in our bin. There it is. And now let's do some examples. So what you're looking at is a query for the graph. And it is basically kind of a subgraph. It's a view of this particular graph. So in this query, we're saying, okay, I want you to place this abstraction called a slot, meaning where I'm going to ask for this kind of exclusive set of resources in the graph. It's like taking a pin and sticking it there and being like, this is the shape of resources that I want you to find somewhere across this graph. So that's the shape that Fluxion is going to look for. So for this case, saying, okay, I want you to find me a cluster. We have the cluster. And for my slot, I want you to have a rack that has 2 nodes, 1 socket, each socket with 1 core. I also want you to have a quantum device that has a QPU with 2 qubits and 1 coupler. And this would be like my request for work. Now, this would normally be requested, via a command line interface. It would go through the Flux core, and it would eventually get to the scheduler in a representation like this. We're just doing it raw, kind of willy-nilly directly because we're interacting directly with the APIs, and that's actually pretty cool about Flux. So let's do this particular match. And there it is. So what we just did, and I can show you the code, is we matched those resources against the graph. This is the result that using the Go SDK to Fluxion returned. It said, okay, job ID is 1. It's not a reservation. You didn't ask for reservation. The overhead of doing the match was very, very small. The time is now. And guess what? Here's what the allocation looks like in a representation of the graph. This is the graph that we looked at first. This has no traditional CPU stuff in it. This is just the gateway, QPU, qubit. And in this time, we're modeling IBM Fez, IBM Marrakesh, just those 2, actually. I think I just chose those 2. Okay, so what you just did not see is that I exported my token to the environment as IBM Cloud Token, and then I authenticated. And what we have here is we have a test that is basically doing the same thing that we just did, except it's interacting directly with qrmi-go, so it's going to actually be calling IBM Marrakesh. And so it was about 11 to 14 seconds I started talking a little bit in, but we can see the same interaction happened, except this time we allocated the resources from our Fluxion graph that were specific to quantum, specific to IBM Marrakesh and Fez. And because we're using a match first policy, it makes sense that we got IBM Marrakesh because that was found first in the resource graph. And it looks like it ran in 17.21 seconds, a little slower than last time. I've seen 11 and 14 seconds. 17 seconds is not super great. Let's see what we got in the documentation here. Yes, so this one ran in 11 seconds. So they must be busy today. Anyway, this was the prototype that we created first, just as a proof of concept that we could do the match, submit the work, get back the result, and the next step after this was integration of the same idea, but in an official Kubernetes scheduler plugin. We are going to talk about that too. So once we had this particular fluxion-quantum demo working, we wanted to move into the Kubernetes space and actually make a custom scheduler plugin that would be able to schedule pods in Kubernetes and interact with these quantum APIs. And so we took our initial Fluence project from 2021. We did this first prototype fluxion-quantum, and then we turned it into what we now think of as Fluence 2.0, quantum-aware Fluence that is able to co-schedule QPUs. Let's take a look at what that looks like. All right, so now let's take a quick look at Fluence, the custom scheduler plugin. So I already deployed this, but I want to quickly show you how I did that. Now there is an image that's associated with this repository where we build our custom plugin. So you don't have to build it. So I have instructions here for making an image. You don't have to do that. Deploy it. In this example, I just created a kind cluster. Again, you don't have to do that. Okay, so to deploy it, we applied this YAML file. You can find this in a repository. This has Fluence and all of the kind of dependencies that it needs. Now, there's kind of two examples I can show you. There's a pod group, and then there's the quantum example. The pod group is basically going to schedule using native gain scheduling 2 pods. That's not what this meeting is about, so we're actually going to skip over that. Now, we're going to jump to quantum. And so to get quantum to work, we basically deploy Fluence, and we tell it that it also has custom resources in the graph. So let me show you what that looks like. This is a cool design, I think, because the way that we created it is that we're able to add these arbitrary custom resource types that are added to the Fluxion graph dynamically and then can be queried over and allocated. So in this case, we're saying, okay, let's add IBM Fez and IBM Marrakesh with some number of qubits, vendor, and then a little bit of metadata. And then the daemon set is what's going to deploy a device plugin to the nodes. And this is really just to kind of model that there's an API quota available, specifically the one that we provided. I need to make the note, this is only to allow the resources in the YAML, and the actual scheduling and kind of the control of the resources being done by Fluxion. So this is just kind of a design beat. And I can answer more questions about that if there's interest. Okay, so one quick thing that I'll show you is that if we look at the device plugin, here we see that Fluxion has its own space, and it's saying, okay, for QPUs, I have 1,000. That's an arbitrary choice based on some API quota, maybe that you want to enforce. Let's now apply a quantum pod. I'll quickly show you what that looks like. Here is our quantum pod. The really only major differences here are we're saying, okay, the scheduler is Fluence. Here's my qrmi sampler. So qrmi-go is actually implemented in this application. And this is an application that we made just for this demo. It's going to run a little kind of analysis thing. And as I mentioned, all of the credentials are these values from the secrets that I own, nobody else. And importantly, here's how we're asking for resources. We're saying, okay, for requests and limits, I want a Fluxion, fluxframework.org QPU 1. So let's do it. Let's apply the quantum pod. So if we do kubectl, I'll get pods. It's going to be creating. So this is, pulling the container. We'll wait for that to finish. Running. So let's do kubectl logs sampler. And we'll leave it hanging. Submitting the job to IBM Marrakesh. I hope IBM Marrakesh is working right now. Okay, we're back. So it looks like our sampler did run. And I didn't put a time on this, but let's see, 38, 39. Yeah, so that took a little bit, that was about a minute. Not terrible. It's not as fast as it's always been. And this is a really cool result. So this was Fluxion running in Fluence in Kubernetes via custom scheduler plugin. It has a cleanup as well. And then we can look at the logs. So kube system, and then we'll look at Fluence. What's the name of it? 75. you'll see there's a request to cancel a job. So when the job is canceled, that frees up the resources in the resource graph, and we're done. From a user standpoint, you're basically going to be asking for an additional resource type, a fluxion fluxframework.org/QPU. And then in practice, you submit your job, you run the pod, we saw this in the demo, and then you look at the logs and you see that you got it. So for the live end-to-end demo, what we saw is that we instantiated the graph, we did the match, we got the allocation, the qrmi job ran, the job owned the credentials, and then we got back a result in the log. And in my first demo, it was 11 seconds, and in another run, it was over 100. So there's a little bit of latency sometimes, it seems. So how this works, just to make it explicitly obvious, is that when we're first bringing up the custom scheduler plugin, we're getting the nodes from the cluster. So that would be equivalent to kubectl get nodes. We're also defining the fluence resources. So these are the QPUs. We're putting them together into a common resource graph. We can then match against it and we can get both nodes and the backend. And I need to again state that there is a deliberate boundary with respect to credentials, that they stay within the user space. This is immensely important for a multi-tenancy setup. And for those that are skeptical, I totally get it about quantum. Is it going to be useful for science anytime soon? The answer is I don't know, but I can tell you that working on system software, we are responsible for predicting the future and in imagining these futures and designing what is needed for them before the users actually need it. Because by the time they need it, they're going to say, hey, I need this yesterday. And we're going to say, well, good thing we thought of it 3 years ago because we are ready. We have this done. So the time to be thinking about this, the time to be working on this is now. And I want to point out this paper that basically built a model for different devices and was able to bring down extremely the variability in the response. I thought that was really cool. Okay, so next steps. What are we focusing on? So we want to get a better understanding of the kind of workloads that are run in different contexts, different use cases. I am personally totally new to working with quantum. I think a lot of folks on my team are too. We want to get an understanding of not just interacting with remote APIs, but also our local devices at the lab. We're going to extend Flux integration. So right now, integration is with the Go SDK, and it's in Kubernetes. We do want to have pieces in Flux core that can support the local devices. We, of course, want to explore our collaborations and present our work. And the fun part is really talking to all the folks here and getting feedback from you. And this unifying insight, again, is that although it's not useful now, it's going to be in the future. So let's work on it together. So thank you for having us today. I will take questions, and however you can reach me, email, Slack. It's been a pleasure.